Now let's think about what happens if you release a real pendulum. It's not an ideal pendulum, so it's going to lose energy. With every oscillation, every half oscillation, it's going to lose energy. So let's say the pendulum starts here and is released. What's going to happen? It's going to move back here, but it's not going to quite reach this position. It's going to maybe go here. And then it's going to come back and maybe be here. And then it's going to maybe be here and here and here and here and so forth. Okay? So what happens between the start and the first extreme point after the start? Okay, call these extreme points. When you're here, you have all this potential energy. So here's your total energy at the start. Call that energy total start. By the time it gets over here, it's lost energy. And now its energy total is here. Then it swings back to this point, and we go up here, and its energy total is here. And then it's over here, and then it's over here. Okay, now why is that the energy total? It's because the kinetic energy at each of these points is zero. This is where it stops. Then it goes over here, stops here. Here it stops, here it stops. So you have this constantly decreasing total energy with the kinetic energy sort of following along. Kinetic energy is zero at every one of these points. And I don't want to try to draw that because the drawing really would need a third dimension to develop in time. But you get the idea. You have a system that's losing potential energy because of non-conservative forces. Okay, so energy is lost to non-conservative forces. You remember that if non-conservative forces are doing negative work on the system, then delta KE plus delta PE will progressively decrease. Now we're seeing similar behavior with the ball on the two ramps. Goes down one ramp, up the other, and so forth. What would the potential energy for that sort of system look like? And we'll take a look at that in a second. We have two ramps, one steeper than the other, and we start a ball rolling here. It'll end up here on this ramp, assuming there are no losses to non-conservative forces. So if delta WNC is zero, we have maximum position here and here, and we have maximum potential energy at both of those positions. And we'll have the ball will go from here to here, back to here, back to here, forever, if there are no non-conservative forces. And if you can figure out a way to make that actually happen in the real world, that'd be very handy. I wish you'd do that. Okay, nobody's invented a perpetual motion machine yet. I've had a couple of people come by here thinking they had, and you know, I always take those things seriously. You never know, but at least you know, I'm 99.many9% sure that they haven't, but I try to analyze everything as clearly as I can. Sometimes I convince them, sometimes I don't. They've never gotten violent on me. They're always good people. Okay, anyhow. Okay, so start to here to here to here. Now, energy diagram. And I actually meant to develop this as I was talking, and I did, but I just forgot to hit the record button, so I'm going to just go back over what I did. Has the advantage of being shorter. So we can draw the maximum potential energy right here, and that's equal to the maximum energy of the system. If delta WNC doesn't change, then the mechanical energy is always equal. Actually, I don't need a max on that. The mechanical energy is equal to the maximum potential energy. Now, clearly, when the ball goes down the incline, it loses potential energy. When it climbs back up, it gains potential energy. Our potential energy is a function of x, and it's going to be measured relative to the low point, meaning at the low point, the potential energy is 0. So the potential energy goes from whatever it is here to 0 and back up to its maximum. We see the orange potential energy vectors, arrows. Energy is not a vector quantity. These arrows representing the potential energy from point to point. We see it steadily decreasing. And we see the kinetic energy vectors, which have to make up the rest of the mechanical energy, increasing correspondingly. Which leads us to the very intuitive conclusion that the object has to speed up when it goes down this incline and slow down when it goes up this one. Did I say up? Speeds up when it goes down this incline, slows down when it goes up this one. We'll get that directly out of the energy analysis, and then we can test it. And of course, it works out just as we expect. Now we might ask, it'd be kind of interesting, what if these ramps were curved? So maybe I'll have room to at least sketch a system. Let's say this ramp curves like so down to a low point, and then this one comes up and does some sort of a sigmoid thing. And let's get this up here. I don't have very good perspective on the board, so I can't really tell where horizontal it is, but let's just say we move from this position to this position. Okay? Now, how's that going to change the potential energy versus position graph? We're going to have a graph that in many ways is very similar to the one we just did. We're going to start over here with some potential energy. We're going to end up over here with the same potential energy. So we're going to have this total energy function. So we're going to start here and end here. Now, you weren't able to see that because I was standing in the way, but okay, here's our potential energy function. Here's our x, and here's our E total. It would be a good exercise for you. I'm not going to do this for you. It would be a good exercise for you to think about how the potential energy changes here and here. What does the graph look like? It's not going to be a straight line graph like it was up here. And you could also think, why is it a straight line graph up here? Be a very good exercise for you to do that.